Today we will discuss Oersted experiment. What are the Oersted experiment's observations? What was his conclusion? And then Biot Savarts law. What is Biot Savarts law? And how we can apply this to different cases there. We'll start with application of Biot Savarts law to a circular current carrying conductor at a point on its axial line. Then we'll use that one to find magnetic field due to circular current carrying conductor at its center, and also some other cases. Oersted performed an experiment in which he passed electric current through a wire and a magnetic needle was kept nearby. And in his experiment he found when electric current is passed through the wire, the needle shows deflection. His observations were when he passed electric current through the wire in a direction south to north, through the wire kept over magnetic needle. Then he found that the north pole of the needle gets deflected in west direction. When he passed electric current through the wire in the south to north direction, then he found that the north pole of the magnetic needle gets deflected in the west direction. So it will get deflected like this, in this direction. When he reversed the direction of current, then the direction of deflection also got reversed. Like when he passed from north to south and was kept over the needle, then it gets deflected in the east direction. After this, what he did, he put the needle over the wire. So this time, again he passed electric current in the direction, say south to north, through the wire which is kept below the needle now. So when he passed electric current in the south to north direction and it is now kept below, then it shows deflection in the east direction. Again, when he reversed the direction of current, the direction of deflection also got reversed. That means now when he is passing current from north to south and is kept below, then the direction of deflection gets reversed. That means it is in the west direction. From his observations, he concluded, first of all, that deflection of the magnetic needle, this indicates presence of some magnetic field. There was no magnetic substance kept nearby. Like that time it was assumed that magnetic field is only produced by magnets. And magnets or the magnetic substances which we are keeping there nearby. So here there were no magnetic substance kept nearby this magnetic needle, and still it was showing deflection. So obviously the cause of magnetic field experienced by this needle is something else, because there was no magnetic substance kept nearby. So then he said that it is due to electric current, and his conclusion was supported by the fact that the deflection is there only when the current is passed through the wire. Second thing, that the direction of deflection gets reversed when the direction of the current is also reversed. So obviously it is depending on electric current. So from his experiment, Oersted concluded that electric current produces magnetic field. This is the importance of the Oersted experiment. He was the first one to indicate that electric current produces magnetic field. If you want to remember this direction, like sometime you may get questions that if the current is passed through the wire from south to north direction and magnetic needle is kept below the wire, or wire is kept below the needle, in that case in which direction the needle will show deflection. So these are the 4 cases there that you should remember. And just to remember all these, best is just remember the word snow. If you remember this word, you can get any of these. You don't have to memorize all these separately. How we are getting this? When current is passed from south to north through the wire kept over the needle, then the north pole gets deflected in west direction. So it is your south, north, N, O, and this W. So this is your snow. So if you just remember this snow, you can easily say when the current is passed from south to north direction through the wire which is kept over the magnetic needle, the needle gets deflected so that north pole faces west. And if you remember this one, you can get any other case also. Like if I change the direction of current, if you make this one as north to south, so south to north direction, I have changed to north to south. It remains over. So now it will be east. Because if you are using one statement, then you will get the same meaning if you are using 2 negative statements. Here, south to north, I have changed to north to south. Over is kept same. So west we change it to east so as to get the same result. Similarly, if it is your south to north and now it is kept below, so this time I have changed over to below, so west will change to east. And the last one, if it is your north to south, it is below. So now you see, south to north I have changed to north to south, over have been changed to below. So in that case, this one will remain same. That means it will be west. If you remember this, you can easily write the direction of deflection for any of these cases or any problem or question which is based on these observations if it is asked in the exam. After Oersted has concluded that electric current produces magnetic field, then the different scientists started working on that magnetic field. Biot and Savarts, together they have given the law that the magnetic field produced due to a current element. Current element we take, suppose you have a wire which is carrying current and suppose I is the current. We take a small element of that wire or the conductor which is carrying current. So the product of current and the small length through which that current is flowing, that we call it as the current element. Here we can take IDL as the current element. So the statement of the Biot Savarts law was magnetic field intensity at a point due to a current element is directly proportional to the magnitude of the current element, inversely proportional to a square of the distance between the observation point and the current element, and it is directly proportional to sine of the angle between the direction of current element and the line joining the current element to the observation point. So if we represent this mathematically, suppose this is your XY as the wire which is carrying current I. We take a current element IDL and magnetic field due to this at a particular point P, which is R distance apart from it, is dB. So in this case, by Biot Savarts law, we can say dB will be directly proportional to IDL because magnetic field due to current element is directly proportional to the magnitude of the current element, inversely proportional to R square, directly proportional to sine theta. Theta is the angle now between the direction of current element and the line joining the current element to the observation point. So you have these three expressions there. If you combine these, you will get dB proportional to I dl sine theta by r square, or dB will be equals to mu naught by 4 pi I dl sine theta by r square. Now this mu naught is called permeability of free space or vacuum. This is a similar term what we have got as the permittivity in case of the charges they are kept in the medium. So here this permeability will also be representing how the force or the magnetic field between the current elements gets affected when we introduce some medium between the two current elements or the observation point and current element. So this is your mu naught, which is the permeability of free space or vacuum. The value of this mu naught by 4 pi, this is your 10 to the power minus 7 Tesla meter per ampere. So this is the value of mu naught by 4 pi. This is a constant of proportionality used here. Magnetic field intensity, if you consider, this is the force experienced by current element placed at that point. Just like electric field intensity at a point was the force experienced per unit positive test charge placed at that point. So here also it is the force experienced per unit current element placed at that point. Or this is also expressed in terms of unit north pole kept at that point if you are taking magnetism there. So this is the vector quantity. So this is just giving you the magnitude. And if you want to write the expression for magnetic field intensity in vector form, then we write this one as mu naught by 4 pi I dl vector cross r cap by r square. R cap is unit position vector for this current element there. So this is your r cap. Now this, if I write, that means it is given by the cross product of the vectors there. And if we write this as mu naught by 4 pi I dl vector cross vector r divided by r cube, as r cap can be written as vector r by its magnitude. Unit vector can be written as the vector divided by its magnitude. So this is the expression. So that means this is dB. Either you can write in this form or it can be written even in this form in terms of the unit vector, in terms of the position vector there. So this is how we express magnetic field intensity at a point due to current element. Now we can use Biot Savart's law for different cases. You have suppose the wire which is carrying current and the wire is a straight wire. It may be a circular conductor there which is carrying current. We can find magnetic field due to the circular current carrying conductor at a point, maybe at the center on its axial line or any other point there. Remember, magnetic field value, magnitude we can give by this expression, direction will be given by cross product. This is the cross product of the two. So you will just take cross product of current element and r vector. With that cross product, you can easily get the direction of magnetic field. Let's take application of Biot Savart's law to find magnetic field intensity due to a circular current carrying loop at a point on its axial line. We are deriving it in general, that is on axial line. We can get the different conditions that if the observation point is at its center, what will be the magnetic field? If the observation point is at very large distance, then what will be the expression? All we can get it from this derivation. So let's try to find out magnetic field due to a circular current carrying conductor at a point on its axial line. So suppose we have a circular conductor, it is carrying current I, and we want its magnetic field at a distance x on the axial line of it. Capital R we are taking as the radius of this loop, and let's consider one current element IDL. IDL is here, and the distance of this current element to the observation point is a small r. Suppose this one produces magnetic field dB here at the observation point. Then by Biot Savarts law, we can write dB as mu naught by 4 pi IDL sine pi by 2 by r square. Why is it so? Because here you can see this current element is IDL, current element direction, and the line joining the current element to the observation point, that one will make an angle of 90 degree, because the direction will always be current element, that will always be tangential there. So this one will be making an angle of 90 degree. So we have taken mu naught by 4 pi IDL, and this sine 90 we have taken. And r is the distance, so it is your r square in the denominator. So this can be written as your mu naught by 4 pi IDL by r square. This is dB. Now this dB will be in this direction. Why? Again, it will be given by the cross product of the current element and this r. So it has to be perpendicular to this r. So this one we have shown in this direction as dB, which is at 90 degree to the value r. We can resolve this dB in two directions, one along the axial line and other perpendicular to the axial line. If this one dB, that is the magnetic field due to the current element, is making an angle theta with the perpendicular direction, component in the perpendicular direction will be your dB cos theta, and in this direction it will be your dB sin theta. So we get dB cos theta and dB sin theta. Now if you consider current element which is diametrically opposite to this current element IDL. So here this will be the direction of the current element. If you consider the magnetic field due to this, it will be somewhere in this direction, dB. So again this dB, as you have taken just the diametrically opposite current element for this loop, so this one will also be making the same angle theta with the perpendicular direction to the axial line. So this dB, if it is resolved, this is also dB cos theta and dB sin theta in the two directions. dB cos theta, they will cancel out one another because they are in opposite direction, they are equal in magnitude. So the net magnetic field at the point P will only be due to dB sin theta. So this one, dB sin theta, will give net magnetic field. So if I want the total magnetic field, it will be integral of this quantity. Do remember one thing, it will be dB sin theta due to this dB as well as this. But when we are taking the total magnetic field, we will not take it as 2 dB sin theta and integrate, because then you are adding algebraically as well as by using calculus. So we take dB sin theta only and we integrate it for the entire loop, and once you integrate it for entire loop, it will take care for all the current elements which we get, which is on the wire at different points. So it is only dB sin theta integral. Second thing, you remember, suppose if I take this triangle, here this angle how much we have taken? 90. This is also 90. This is the angle between the radius and the axial line. And this one is theta. So if you look at this triangle, the sum of the angles will be how much? 90 plus theta. It is more than 180 degree. Is it possible that we can have a triangle whose sum of the interior angles is more than 180 degree? Remember, sum of the interior angles of a triangle is 180 degree only when it is lying on one plane. Here in this diagram, if you see, it is not on one plane. The current element, if you consider, it is on the axis there. It is in the tangential direction to this. It is just like, suppose I take the loop on the plane of the board. If the loop is there on the plane of the board, suppose it is like this, and it is carrying current this way, so current element direction is this. This is the center, this is its radius, and now if I take a line joining the current element to the point on the axial line, because the axial line will be this one. So if you take this direction, tangential direction and this one. Remember, if I take this one, I put no matter in which direction, it is always at 90 degree to this. So this angle is 90. It is in this particular plane. Whereas other one, which is the axis, the center of this loop and the axial line, this will also be 90. But they are in different plane there. So that is why you can have this case where the sum of the angles may be greater than 180 degree. It is not on one plane. So here, if you consider, this is your dB sine theta integral, and now if I put mu naught by 4 pi I dl sine theta by r square integral, and how you will integrate it for the entire length. So this integration will be 0 to 2 pi r. This can be written as mu naught by 4 pi I by r square. Sine theta, I can write this triangle, if you take it, is capital R by small r. It is perpendicular, this is the hypotenuse. So it is r by r, and then integral dl 0 to 2 pi r. So you have integration of this one from 0 to 2 pi r, mu naught by 4 pi I dl sine theta by r square. And this sine theta, if I am writing, it is capital R by small r. So this is your integral of this 0 to 2 pi r. This is your mu naught I by 4 pi r cube. Integral of dl will be L. We have to put the limits as 0 to 2 pi r. So if you substitute it, it is your mu naught I r into 2 pi r divided by 4 pi r cube. Ultimately, it is your mu naught I r square by 2 r cube. Now you see, this r square, small r square, can be written as capital R square plus x square. So if you substitute it here, what you will get? Mu naught I r square by 2 r square plus x square power 3 by 2. This is the value of magnetic field. This is magnetic field on the axial line of a circular current carrying loop. Now, if you take the different cases here, magnetic field on the axial line is B equals to mu naught I r square by 2 r square x square power 3 by 2. If x is 0, that means our observation point is at the center of the loop. That means magnetic field at the center of the circular current carrying conductor. That we can get if you take mu naught I r square divided by 2 r cube, and finally it is your mu naught I by 2 r. This is the expression for magnetic field at the center of the circular current carrying conductor. Second case we can take, if x is very large as compared to r, so then B will be mu naught I r square by 2x cube. This will be the expression. So this will be the expression for magnetic field due to a circular current carrying loop at a point on its axial line which is far off. Other cases what we can take, suppose the loop which we have taken has capital N number of turns. The loop may not have only one turn. So suppose capital N is total number of turns. So in this case, B will be equals to mu naught Ni r square by 2 r square plus x square power 3 by 2. Directly it will give you the value of the magnetic field there, which will be n times magnetic field due to single turn loop. Here we have also one term. We can write mu naught n I. Now suppose if I multiply it by pi, it is this term. Now this term is the area of the loop. So this is your mu naught Nia divided by 2 pi r square x square power 3 by 2. Here we can write this one in terms of the magnetic dipole moment. This term, current into vector area, that is the area of the loop, current into area of the loop, that is your magnetic dipole moment. If it has n turns, then the total magnetic dipole moment will be capital M. So this will be this 2 pi r square x square power 3 by 2. This will be the magnetic field intensity in terms of the magnetic dipole moment. Let's take one simple example or application of Biot Savarts law. Magnetic field at the center of a circular current carrying loop. So suppose we take that I is the current through this circular loop and its radius is capital R. We want its magnetic field at the center. So in this case, magnetic field due to the current element at the center, suppose it is your dB. So dB will be equals to mu naught by 4 pi I dl sine pi by 2, because the angle between current element and the line joining current element to observation point is 90. So this divided by r square. So this is your mu naught by 4 pi I dl by r square. This is dB. If you want total magnetic field, we'll have to integrate it. So we'll integrate this one. So 0 to 2 pi r. And this is your mu naught by 4 pi I. Integral of dl will give you ultimately 2 pi r by r square. And this is your mu naught I by 2 r. So this is the magnetic field at the center of the circular current carrying loop. Let's take another example. Suppose we want to find magnetic field at the center of this loop. It is a semicircular portion and these are the straight part of the conductor which is carrying a current I. So magnetic field at this point we can get as magnetic field due to the portion AB plus magnetic field due to the semicircular portion. So that means this is due to BC, that is semicircular portion, and magnetic field due to the portion CDL. For this part, magnetic field, this is your mu naught I dl, and now the angle between the direction of the current element and the line joining the current element to observation point, this will be same. So this angle is 0 divided by 4 pi, whatever be its distance which we are taking, any element if you are taking, this will be say x square. Suppose if I assume that this element is at a distance x. So we'll integrate for any part of this one. So since this magnetic field due to the small current element lying on this straight conductor, that will be 0. So contribution due to this part will be 0. Due to this semicircular, now again let's take, it is your mu naught I dl by 4 pi r square, and now we'll integrate this one. As we have done in the previous case, we have integrated over the entire loop. But this time it will be only for semicircular portion, so it is your pi r. And again for this part, this is your b will be 0 because it is again mu naught I dl sine 0 divided by 4 pi. Again, suppose if I take any element at a distance y here, so it is your y square. This term is also 0, so it is 0. And now this is your mu naught I pi r by 4 pi r square plus 0, or mu naught I by 4r. In fact, it is the magnetic field only due to this semicircular portion. And for that, we have just changed the limit of integration. In case of full circular loop, we have taken the integration from 0 to 2 pi r over the entire length, and now it is for 0 to pi r. Now this result we can also get magnetic field due to circular loop at its center. This is given as your mu naught ni by 2r. N is the number of turn. If it is semicircular, what will be the number of turn there? Half. N will be half for semicircular loop. So if this is the case, then B will be how much? Mu naught half I by 2r, and that is your mu naught I by 4r. This will be the expression for magnetic field. Now this formula you can use for any case, whatever be the number of turns. If it is 2 turns, 3 turn, 10 turn, 100 turn, then it's okay. But even if it is the part of the circular loop, it is not the complete loop there. Like here it was your half. Suppose it is only 1/4 or it is 3/4. We can put the value of n there correspondingly and get the magnetic field. So these are the applications of Biot Savart's law for the different cases.